Project network times are not a schedule until resources have been assigned. Cost estimates are not a budget until they have been time phased. These are the two really truisms of project management. We're assuming that the resources will be available when they're needed, and that's usually not the case. And of course, when we put in projects into our system, then for sure we start losing the availability of those same resources as they're being desired to be used over multiple projects. Furthermore, you really don't know what your budget's going to look like until you've actually put in align your estimates in your work breakdown structure to the costs associated with that work. And that way you have a time phased in budget plan, so you know when you're going to need the necessary resource called money to get your project going. Initially, we'll talk about the resource problem, and then when we finish up this chapter, we'll talk about the time phase budgets and how to actually schedule our budget plans. So let's first take a look at the resource problem itself. We always want to try and optimize our resources, and so what we try and do is level or smooth the resource, and we try and even out the varying demands of resources by taking that slack that we've established in the last chapter, or chapter 6, and use that as a way of managing resources over the life of the project. Ultimately, we might have to lengthen the project if we don't have the resources available, if the manpower is not there, if the staffing's not available, if the equipment's not available to do the task. If we don't have those things in place, we might actually have to take and make our project last longer so that we can actually get the resources we need when we need them. These are the typical types of project constraints you can see. Of course, we see technical and logical constraints all the time. We're not going to build the road until we survey the land. We're not going to survey the land until we get the contract that we can buy that land. So those are clearly logic constraints or technical constraints to that very simple project. Sometimes there's physical constraints. We saw in the example of laying the pipe along the highway that we're not going to be able to lay the pipe until we actually dig out the trench. We can't backfill in that trench until the pipe's in place. So there's going to be some physical constraints on how little bit we can dig up before we lay pipe in, due to maybe the pipe length, due to laws and regulations regarding safety in trenches. So there might be some physical constraints associated with a project of laying pipe down the roadway. Maybe we have resource constraints where we don't have the people we need or the equipment we need to get that next task started, or even get a project started underway. So as you might imagine, resources take on several different types. People, sometimes they're materials and supplies, sometimes they're equipment, and sometimes there's actually a money resource problem. We don't have money to do the next phase of the project because that budget hasn't been authorized. Here are some examples of technical and resource constraints in the top two processes. The first one seems to be building some sort of a building. You won't put a roof on until the frame is up. We won't put the frame in until we've poured the foundation. I think those are pretty logical technical constraints. The second one is maybe some sort of a software project where you won't test the software till you coded the software. You won't actually write your code till you actually design what the software is going to do. When we get into resource constraints, we can see when we have enough resources, we might, in fact, in the case of planning this party or reception, get enough people around to help us decorate the hall, hire the band, and purchase refreshments. Those can be done in various sequences. They can be done in parallel to some extent if you have enough resources. B represents the ability to multitask or have enough people available to decorate the hall, purchase the refreshment, or hire the band. You may run into a situation where there's less people available, and it might be you and that other person that are responsible for hiring the band, and then later on you'll do the hall decoration and purchase the refreshments and bring them in to the reception. So you can see that that can be done both in parallel or sequentially. There's a reason why we've been looking at the project priority matrix. It pops up a lot in project management. And so we'll use our project priority matrix to determine whether this project is time constrained or resource constrained. In a time constrained project, as we said before, we're going to impose a specific completion date. And so time is fixed, resources are flexible, and additional resources that are required to ensure the project meets the schedule can be available. In a resource-constrained project, we've got cost limitations. Resources are fixed, time is flexible, and we don't have enough resources, and if we start going below a certain minimum threshold, we will in fact delay the project. So if you have a project priority matrix that looks like this, you would consider this to be a time-constrained project where we've constrained time, and I suppose you can either enhance cost or enhance performance and accept the other. When we constrain resources, we typically are constraining our cost, because if we had unlimited cost available to us or unlimited money available to us, we probably could find the resources to get the project done. So you can think of a resource constraint as a cost constraint on your project, and then again, either we'll try and enhance performance based on that constraint and let the project take as long as possible, or we'll do what we can to find time-winning strategies, but we'll accept less of a project from a performance standpoint. When we go ahead and do these problems either with by hand or with a computer, we've got to make some assumptions about what we're going to do regarding our resources and regarding our tasks. And if we go back to our holding true to a form on what we mean by an activity, we would see that we wouldn't allow activities to be split. Once an activity is started, we'll assume it's carried to completion. There's lots of penalties and problems why you might want to split activities. You do those at your own risk and peril, and we'll talk about multitasking and splitting activities later in this session. We'll also assume that once we start a work, we can't add more resources to that particular activity. Again, that holds a line on what it takes to get that project done under normal conditions, what it takes to get a specific activity done under those same conditions. If we're starting to add more resources to that to speed up that activity, well, that's a strategy, but it's a strategy we use in a process called crashing, which you'll see in the next chapter. Along with these limiting assumptions, we've got some risk assumptions that hold true in the most case, but by all means, your risk management plan might suggest that some of these things pop up as well. But we'll assume that activities with the most slack pose the least amount of risk in terms of schedule, and reduction in the flexibility doesn't increase the risk. So when we actually start crashing activities or reducing the number of days that we're allowing for slack, we're not increasing the risk. And the type of activity, whether it's easy or complex, doesn't affect the risk. Let's take a look at time-constrained projects, and then we'll show an example. So in a time-constrained project, we've got a situation where the project must be completed by a certain date, and then the best we can do is use whatever leveling techniques that are available to us to smooth out the resource demands. And we'll do that by using the slack and activities that aren't critical. And our hopefully when we're done, we'll reduce the peak demand on our resources, we'll reduce the total number of resources required over the life of the project, and we'll minimize the amount of fluctuation of resource allocation. So let's look at an example. Let's take a look at this example. It's the example of a botanical garden project where we'll start out with design. After we're done designing it, we'll do a layout and scarify of the area. Then we can do the walkways, and we can do the irrigation, and we can do the fence and walls. And once the walkway is completed, we can do the lighting. Once the irrigation and fence walls are completed and the lighting is completed, we can do the planting. So you can see there's slack in two activities, irrigation and fence and walls. Also shown here are the number of backhoes required for each task. So in the slide below, we've done an initial resource load for the project. No backhoes are required when we do the design. We need 2 backhoes to lay out and scarify. Then we need 1 backhoe each for walkways and irrigation and 2 backhoes for fence and walls. And we need 1 backhoe for lighting, and we need 3 backhoes to do the planting. So our goal here is to figure out what we can delay and minimize the amount of backhoes we need to get the project done. Try this when you work on these types of projects, these time-constrained projects. There's no heuristics or rules you can follow. You just got to play around with it and see if you can meet the goals of reducing the number of resources required for the project, reducing peak demand, and reducing fluctuations. So you can see here that the demand starts at 2 backhoes, goes up to 4, then down to 1, and back up to 3. So think about it for a second. What could you change without losing the final date of 24 days into the project? What can you change in this project in order to meet the requirements of reducing the number of resources required? Let's take a look at what we can do here. Again, I got a repeat of the Gantt chart in the first top slide and a repeat in the initial resource load based on that Gantt chart. But take a look at what I can do here. If I go ahead and do the walkway and I go ahead and do the irrigation, the 2 backhoes that I had to do the layout and scarify, I can use. I can delay the fence and walls because I have slack. And then I can go ahead, after I finish walkways and irrigation, I can bring another backhoe onto the site. So I'll have 3 backhoes total, and then complete the fence and walls, which require 2 backhoes. And that single backhoe that I bring into play can then now do the lighting, and then I've got the 3 backhoes I need to finish up the job and do the planting. I think the last problem we just showed you demonstrated what happens when we go ahead on time-constrained projects and see if we can use slack as an opportunity to reduce our peak demands for resources and reduce the fluctuation of those resources. So you can see what happened, the advantages of doing that. We've gone ahead and reduced the peak resources from 4 to 3. We've reduced the required resources over the life of the project then, and we've also reduced that fluctuation. We started with 2 backhoes and we went to 3. The disadvantage is we lose some flexibility because we took away the slack on one of our activities, and as a result of that, we've increased the number of critical activities and made our project network that much more sensitive. When we look at time-constrained problems, there's no real common rule set to use. It's really just a trial and error process. But when we get into resource-constrained projects, we can follow a rule of thumb that will at least get us to an optimal solution. There may be other optimal solutions that work as well, but if we're following these heuristics, we know that we won't run into any problems with the project, and we won't introduce any additional risk. So in resource-constrained projects, we're going to limit the availability or quantity of resources available. We'll schedule based on these heuristics for this resource-constrained project, where we'll look at and schedule resources based on which activity has the least amount of slack. If you have 2 activities with the least amount of slack, we'll go ahead and select the activity and schedule the one that has the least amount of duration first. And if I have 2 activities that meet criteria 1 and 2, I'll go ahead and do the one that's listed first in the work breakdown structure that has the lowest activity number. And then we'll use this iteration process and a parallel method in which we'll analyze what we did. We'll take a look at resources, look at resource availabilities, change the slack as we start reducing the slack and use up that slack, and reanalyze our process and follow these heuristics along the way. The best way to take a look at this is to try lots of examples. I'm going to show a few here in today's lecture, but please go ahead and watch the instructional videos I posted along with a guide or score sheet you can use to go ahead and try this along with the instructor. Here we have a project, and we can see right now we've got 7 activities. We have a critical path at the moment that's running from activities 1 into 3, then down to 6 and back to 7. We can see that we're going to take 2 people to do activity 1, 2 persons to do activities 2, 3, and 3, and then 1 person to do the rest of the activities. However, we're going to constrain the number of resources available to us at any given time to 3. So here is our initial project network. I've gone ahead and made a Gantt chart from the project network, and it shows the relationship between the activities, shows the initial slack. Here the slack is shown by white blanks in the Gantt chart. And we've gone ahead and put the resources required for the activities that we've scheduled so far. Obviously, we got to schedule activity 1 before we do anything else in the network. So we've gone ahead and identified the 2 resources required for that activity. And we've identified that as our resource load for days 1 and 2 of the project. We have 1 resource available at this point. So now we need to schedule activities 2, 3, and 4. We only have 3 resources available total, so we got to figure out which one we'll schedule first. Based on the information provided, we'll use the common heuristics of the least amount of slack, the shortest duration, and then the lowest activity number. I think you can see that we need to schedule activity 3 first. It has the least amount of slack of all these activities. We go ahead and do that, and we'll write the number of resources required for that activity to be started and completed, and you'll see it takes 2 resources to do activity 3. We only have 3 resources available, so our hand is sort of forced. Even though we want to start activity 2, we can't, because that has the least amount of slack now. But since we want to schedule people as long as possible, we'll go ahead and schedule out activity 4 and get it done early so that we have resources available later when we need it. And so in doing so, we've gone ahead and lost, at least initially for day 3, any slack available in activity 2 goes away, and this drawing also shows that as well. You can see here in this slide, we've gone ahead and shown what happens when we schedule 2 resources for activity 3, and we've got another activity that we'd like to run in parallel, but we don't have enough resources for. We can see the impact here. Not only do we lose the 2 days of slack originally associated with activity 2, we lose an additional 2 days because we can't schedule the activity until activity 3 is done. So we went from having 2 days of slack, a positive 2 days of slack in activity 2, to having a negative 2 days of slack. The impact immediately is that the project will take 2 days longer, and that's what's represented by this shot right here. We see activity 7 had 0 days of slack, and as a result of delaying activity 2 4 days, we're going to lose 2 days in the project. So when can we schedule activity 2? We can't schedule activity 2 until activity 3 is done. Activity 2 will not be scheduled until the beginning of day 6.